Hello. We are going to continue with the dynamics of circular motion in this chapter and in this video actually. And but before that, let's just rewind what we had obtained in the previous video in this series. What we had obtained is that when an object is moving along a circular path of a certain radius, the object has a certain mass. This is the radius of the circular path, and the object has a mass associated with it. It is moving with a constant speed, supposedly, uh, along the counterclockwise sense in this case, suppose. Then there's a force which acts because of its motion, and that force, the motion contributes to the force. The force isn't created all by itself, and that force is what we call as the centripetal force, and that is usually expressed as mv squared divided by r, and or v is equal to r into omega, omega being the angular speed. So we have mr omega squared, omega being the angular speed. Now, with this information available to us, now there's also the chance that a vehicle, as it moves along a circular path, with the forces involved or associated with it, be it the frictional force, be it of the between the tire and the road, or the air drag, or even the motion on the whole along a curved path, it can cause trouble if the speed is exceeded or if the speed decreases. So you need a certain optimum speed which you need to maintain so as to stay in track, else one might just get off the track. The vehicle may skid, and it may just with losing its track, it may get out of the track, and fatal accidents may occur. Now, in order to avoid that, well, in case of two-wheelers, if you have seen motor racing, then two-wheelers can bend themselves and balance themselves by bending along the curved path. But it's not the case for four-wheelers, the heavy vehicles. They cannot bend on themselves on a given curved path, and that is why these paths themselves, they are bent accordingly to allow a certain speed uh, with which the vehicles can move over them on a turning track or a turning road. Now, this bending of this road is what we term as the banking of road. The banks are especially the edges. If one of the edge, uh, which is usually the outer edge, actually it has to be the outer edge. So the outer edge, now this is a front-on view that I am giving you. The road is probably coming out of the plane on which I am drawing, and the curve is towards this inner side which is in the which is kept low. The outer edge is kept higher than the inner edge of the curved path in which the vehicle is moving. And as I said, this is a front-on view. Let me give you a front-on view of a four-wheeler vehicle. Now, this is not an exact uh, figure that will help you, but to some extent, these are the headlights of a car, and the car has wheels. And obviously, when you see the front-on view, you cannot see all the four wheels. These I'll be drawing two wheels over here in the front, and obviously they are facing you, and these are quite thick wheels that have drawn, and behind them you have two other wheels which are exactly aligned along the same line, and this is the roof of the car, the body of the car, and there's probably a person sitting over there driving it. But let's not go into those details. What we are concerned about is that how we have the car to remain balanced as it moves with a certain speed along this curved path. Now the curve that you are observing, the car is approaching out of the plane of the paper or screen that you are observing. That is, it is approaching towards you, and it will, as you look at it, it will go towards your left. The curve is towards your left, and that is why it will be so the left side, your left side that you're watching, the left side gives the inner edge, and the inner edge is along which the curved path is moving, and that is why this curved path will have a certain radius. It'll have a certain radius, and let this be the center of the track, and from the center to the center of the curved path you have a certain radius, and that radius being r in this case. Now the vehicle and the person in it, they have a mass, and that mass contributes to the weight, and the weight acts exactly vertically downwards. Now this is the weight of the vehicle, and the curved or the inclined track, the bent or banked track. So this is the banking of track or banking of roads. So in this case, you have the weight to be acting vertically downward, but the component of the weight that acts along this line, the angle here being equal to this angle, let this angle be theta over here. Theta is this angle as well as this angle. So this component that you have over here is simply mg cos theta, and that is equal to the reaction force, because the reaction force will always remain normal. So this is the reaction force. Remember, r is the reaction force here, small r is the radius of the curved path, and the reaction force will have two components as well. One of the components, that is the cosine component, that will be acting along the vertical direction, vertically upward direction. So this is r cos theta, while the sine component, perpendicular to the cosine one, that will be acting towards the center, and this is r sine theta. Now this is the component which contributes to the centripetal force, because as we know, the centripetal force is not a force which is created by itself. There is some other force which contributes to the centripetal force, and in this case the force being the sine component of the reaction force. Now obviously there will be some frictional force involved along the path, and the frictional force in this case is supposedly acting along this direction. So this is the frictional force which is acting along the path or along the road, and therefore you will have two components of frictional force as well, because the frictional force is along the incline. And so considering two components, let me give it to you in another ink. And so you have the cosine component of the frictional force. So this is the frictional force over here. This is F cos theta, which is acting along that line, while there will be an F sine theta as well, which will be acting vertically upward. So this is F sine theta. So if this vehicle is to remain balanced as it moves with a certain speed, let the speed be v, it's a constant speed v, and if this vehicle is to remain balanced in that speed, so we have to consider all the factors that are associated, all the forces. Now what are the forces along the horizontal line? So along the horizontal you have the r sine theta, which contributes to the centripetal force, but that's not all. There's an F cos theta which is acting exactly in the opposite direction, but all of that will contribute to the centripetal force, and that is why, which is acting towards the center of the curved path, and r sine theta is acting along that direction, so that has to be greater than the F cos theta factor, such that you have a centripetal force involved. So this is mv square by r. Now along the vertical direction, along the vertical line, you have the r cos theta to be acting upward, and that will be added to the sine component of the frictional force, which also acts in the upward direction, provided the frictional force is acting up the incline, and that must be balanced by the weight. If the left hand side is greater than the right hand side of the equation, then obviously you have the vehicle to be flying off the road, which happens when the speed is greater on most occasions. But that is and what becomes greater in that is that the frictional force tends to, you know, tends to become greater in that case as well, and that results in that lift. So with these things available to us, what we can do is we can just divide each of this equation. So this equation is divided supposedly by r cos theta, and again this equation is divided by r cos theta. Why I'm doing that, we'll be knowing that shortly. Now this left hand side of the first equation that we have, that when divided by r cos theta, what we have is tan theta minus, this is simply f by r, and on the right hand side you have mv square divided by r multiplied with 1 by r cos theta. Let it be as it is. Then you have the value as simply 1 for the vertical equation, because r cos theta by r cos theta is 1, and you have f by r and tan theta, in this case sine by cos, and again mg divided by r cos theta on the right hand side. Now this, let this be equation 1, let this be equation 2. You divide 1 by the equation 2, and all you have is tan theta minus, now the f by r term, this is the friction divided by frictional force divided by the reaction force, and that simply is equal to the coefficient of friction, which is usually denoted as a mu, mu being the coefficient of friction. Will be right, let me just write that for you over here. F by r is equal to mu, where mu is the coefficient of friction. You know this from the friction portion discussed. So coefficient of friction, and then this is divided by 1 plus, again f by r is mu times of tan theta, and this is equal to, on the right hand side, if you divide both the equations, then 1 by r cos theta 1 by r cos theta simply cancels out, and the masses cancel out m by m, but what you're left with is simply v square divided by r times of g in the denominator, and this is a good equation to look at, although it doesn't look really good because on the left hand side you have a whole lot of terms to remember. But this will be easy if you know that the coefficient of friction, that is simply tangent of a thing called angle of friction or the angle of repose, which are mathematically equal. So alpha is simply the angle of friction, or even the angle of repose, which are the same thing uh, when considered mathematically, because physically they may mean different thing, but mathematically they have an equal value, and this is the angle of friction or the angle of repose, and so this term can simply be written as tan theta plus alpha. Tan A plus B gives you that formula that is on the left hand side. But no, this is tan A minus B, because there's a minus sign over here. Had this been plus, then this would have been minus, then you would have had tan A minus B, but the tan A plus B, but this is tan A minus B, B being here tan alpha, for tan alpha, which is there for mu. Now obviously theta is fixed because you cannot change the angle of the road, and angle of inclination or the banking of the road, and alpha is constant for a given coefficient of friction between the tire and the surface of the given road. So which is standardized in case of which is standardized in manufacturing units, such that the roads and the tires are exactly made with materials which have a standardized value, so as to provide you with a constant value of mu. And the radius of the road r, that is small r, and the acceleration due to gravity at that given place, they cannot be changed as well. These are permanent things, and that is why with these permanent values available to us, what we have is a v will be equal to, or v squared in this case, will be equal to rg times tan theta minus alpha. And with these constant values, you obviously obtain a constant value for v. That means, let me write it over here. V is simply equals to root over of r times of g times of tan theta minus alpha, which is giving us the expression for the speed. Now this speed that you have, okay, this is a generalized formula. This speed that you have must remain as such, so that, because we have obtained this for the balanced condition of the vehicle, and so the vehicle must have a specific speed with the specific values of r, g, theta and alpha, such that the vehicle remains balanced. Now consider the case where there is no frictional force involved. Now with no frictional force there, then what do we end up with? Now in case there is no frictional force, what we have is that F, or mu in this case, goes to 0. So without any frictional force, we have mu to be going to 0 or tending to 0. Then what remains with us is that v square by rg will be equal to, the first term that we had is tan theta minus mu was put to 0, 1 minus mu times of tan theta, again mu going to 0, and what that gives us is, what that leaves us is simply tan theta, and this v can be now termed as a VO, where VO is the optimum speed. Now what does this optimum speed give us? Now the optimum speed is the speed with which a vehicle must carry itself or travel along this curved path, so as to have zero friction, or negligible friction, which will not affect its tire or the road to a greater extent, which helps in the longevity of the tire, as well as the material of the tire, its groovings, which helps it to grip the road in a better way, and the road on the whole as well. So with reduced friction, you have a uh, better form of communicating from one place to another, with a speed properly maintained, and these optimum speeds are provided along the road. Now what happens is that if the vehicle moves with a speed which is much greater than optimum speed, then it has a chance of losing its track. Why? Because it experiences a greater form of reduced friction as well as uh, centrifugal force, which is a fictitious force which occurs due to the inertia of direction. And then it also uh, there's a case where, no, this is the other way around actually. V is double greater than VO and V is double less than VO. Then if you look at the equation over here, uh, over to this equation over here, what you get is that with V much less than VO, uh, the left hand side and the right hand side do not balance out, and as a result of that, the vehicle's frictional force, because it is going at a very slower speed, the inclination of this of the road, the banking that is provided, that that allows the weight, the component of the weight, we have mg sine theta in this figure that you have over here. The mg sine theta component acts along this line, right? And with V less than VO, you have the mg sine theta component taking over, and that may topple the vehicle due to its weight, due to that component of the weight which is acting along the downward direction, along the incline. And so what you need to do is you just need to maintain your speed V to the optimum value which we have obtained over here. This is the optimum value, and that optimum value helps maintain the road, the vehicle, and the overall condition um, suitable for driving along that curved path. Well, that's one of the parts associated with the dynamics of circular motion. We'll have more of it in the next video. Till then, thank you for watching.